Everyone, I'm Duan Guanglin from Tsinghua University. It's a pleasure to present our joint work with Peng Laboratory and others, learning enhanced high-throughput pattern matching based on programmable data plan. Pattern matching is a fundamental component in many critical network applications. Its role is to identify known patterns within packet payloads. Typically, pattern matching comprises two parts: simple multi-stream matching and more complex and expressive regular expression matching. There are around 5,000 to 26,000 rules in public rule sets for network applications. Pattern matching covers a wide range network applications, including network intrusion detection, web application firewall, exfiltration detection, application identification system, and so on. For example, in network intrusion detection systems, large sets of multi-string and regex rules are predefined. These rules can scan network traffic to detect signatures of known attacks, triggering appropriate defensive actions. However, current pattern matching systems face major limitations. First, traditional CPU-based or accelerator-based approaches struggle to deliver both high throughput and low cost. Some solutions leverage programmable switches to address cost and performance challenges. Programmable switches can process traffic at Tbps rates with low cost and allow custom packet processing logic. However, they impose computational and storage constraints, like simple operations, limited stages. This forces existing switch-based solutions to be limited to simple multi-stream matching. Complex regular expression matching remains largely unsupported. Furthermore, existing pattern matching systems face a critical common challenge: how to efficiently update a rule to ensure sustained accuracy. When new threads or application patterns emerge, the system must collect traffic samples offline, analyze them based on experts' knowledge offline, and extract new rules. This process is slow, costly, and difficult to automate. Consequently, matching accuracy inevitably degrades over time as traffic patterns evolve. In summary, current solutions face a triple challenge: balancing performance and cost, efficiently handling complex patterns, and maintaining high accuracy through timely rule updates. To overcome these limitations, we define three key design goals. First, achieve high throughput at low cost. Second, sustain high pattern matching accuracy. Third, support efficient and automated updates for evolving traffic patterns. We propose Trochilus, a system that combines the high throughput and cost-effective benefits of programmable data plans with the automated learning capabilities of machine learning modules to simultaneously meet all three goals. To implement Trochilus, our first challenge is how to replace traditional pattern matching with model inference. Collecting large volumes of labeled data for training in network scenarios is difficult and costly. Fully retraining models for new rules is expensive. The key lies in how to fully utilize the expert knowledge in the existing rules. We propose a technique that losslessly converts a given pattern matching rule set into a byte-level recurrent neural network (BRN) module without requiring any labeled training data. The initial BRN inherently encodes the knowledge from the rule set. Crucially, this BRN can be fine-tuned with available training data to improve its matching accuracy over time. To deploy this module on resource-constrained data plans, we deployed data plan model representation, a technique to transform the BRN into lightweight, hardware-friendly module called soft multi-wheel forest (SMF). The second challenge is how to deploy learning modules efficiently on the data plan. Programmable data plans have limited computation and storage. We design tree encoding and entry clustering. These techniques efficiently maps the tree-based module onto the data plan's match action tables to reliably identify patterns that could start anywhere within a payload and are longer than the hardware's native matching capability. We designed an overlapping sliding window mechanism. This can carefully control window size and stride to maximize coverage and precision. Let's delve deeper into pattern modelization. Given a row set, we first convert it into a deterministic finite automaton, DFA. Each byte in the input sequence triggers a state transition in the DFA. Using the forwarding algorithm, we can formalize the score associated with all possible passes for input X. The key innovation is rewriting this forward score into a recurrent form. Recall that the hidden state computation is a forward propagation of a recurrent neural network. Rn is given by equation 2. When u and b equal to 0 and delta is the identified function, the forward score computation of the DFA, as shown in equation 1, become analogous to the forward propagation process of the Rn. To generalize to multi-classification tasks, we can use an MLP layer after BRN as the aggregation layer. On this basis, we convert the DFA with byte format translations into an RN with delta called BRN. Through parameter sharing, this effectively transforms the DFA into an equivalent RN. Let's move to data plan where model adaptation. BRNs are hard to deploy on the data plan due to the floating point and nonlinear operations. Here we introduce semi-supervised knowledge distillation (SSKD). Existing knowledge distillation approaches face two major problems when applied in network scenarios. First, labeled data only accounts for a very small proportion. It is challenging to distill a student module with high accuracy in such data-scarce scenarios. Second, due to the limited computation and memory resources on programmable switches, there are strict restrictions on the selection of student modules. For example, specifically, prior studies mostly deploy tree-based modules, for example, decision trees. So here, SSKD distills the knowledge from the potentially large teacher BRN into the lightweight, soft multi-wheel forest SMF module. It leverages semi-supervised learning, enabling us to train a high-accuracy student module, even when labeled data is scarce. Critically, SMF inference requires only simple match action operations, which is perfectly suited for programmable switches. Please refer to our paper for more details on pattern modelization and SSKD. Each SMF comprises multiple soft decision trees, SDTs. We propose tree encoding to encode SDTs onto the data plan's match action tables. For tree classification, each node in an SDT represents a specific bit position in the input window. The path from the root to a leaf only specifies certain bits, similar to the data plan's native ternary matching. For example, to match pattern class 5, which depends on bit 1, 4, and 8, being specific values, we set the corresponding mask bits to 1 and value bits to the required values. Other mask bits are 0, which stands for wildcard matching. The length of the mask and value fields directly impacts per entry storage. Long keys will consume more table resources. Actually, most SMF-generated table entries contain masks with many zeros, meaning they do not require full n-bit keys. For example, for class 3 and 4, only x1, x2, and x4 are relevant. Other bits can be disregarded, so we can reduce the matching key from 8 bits to 3 bits. We formulate flow table allocation as a table resources minimization problem. The optimization objective is to partition the entire entry set into key subsets to minimize the total storage footprint. For constraints, first, there's no overlapping between any two subsets. Second, the number of subset key does not exceed the allowed maximum number of tables. Since finding the optimal partition is NP-hard, we designed an efficient entry clustering heuristic algorithm to find near-optimal solutions. As mentioned earlier, programmable data plans have a limited native matching length, which is much shorter than typical payload, like 1,500 bytes in Ethernet. Our overlapping sliding window mechanism solves this. When sliding the input window across the packet payload, the matching window length minus the sliding step size must exceed the maximum pattern length. Consequently, we ensure patterns starting anywhere can be reliably detected without missing segments at window boundaries. This mechanism introduces some additional inspection of packet segments, which can increase resource overhead and affect throughput. Network administrators can deploy Trochilus with carefully chosen window sizes based on the available resources in the target scenarios. Through this, they can achieve the desired trade-off between accuracy, resource overhead, and throughput. For evaluation, we focused on answering 3 critical questions. For initial and trainable accuracy, does Trochilus achieve high baseline accuracy, and can this accuracy improve further through training? For throughput and storage efficiency, can Trochilus deliver high throughput while minimizing data plan storage consumption? For manageability, does Trochilus efficiently adapt to new traffic patterns? For experimental setup, we use open source node and Suricata rule sets. Traffic traces are collected from one of the largest public cloud providers. Baselines include traditional pattern matching systems and BOAT. It is remarkable that no existing solution supports full pattern matching in the data plan, so here we choose BOAT as a baseline. We use accuracy, number of table entries, and TCAM requirement as metrics. For evaluation of accuracy and storage, without training, Trochilus achieves comparable accuracy to traditional systems without label data. With training, Trochilus accuracy can be improved by around 10%. By the way, for entry count, Trochilus requires significantly fewer entries than complex rule deployments in traditional systems, or trying to directly map DFAs. This drastically reduces pressure on scarce TCAM resources while maintaining high accuracy. For evaluation of throughput and storage, thanks to entry clustering and the sliding window, Trochilus achieves Tbps level throughput for pattern matching while consuming minimal data plan storage resources. We evaluated Trochilus over multiple weeks of traffic to assess to assess its low maintenance requirements through continuous training. We sampled packet-level traffic for 30 consecutive days at gateways of our large data center and replayed the traffic to the Trochilus system and the Snort system. At the end of each day, Trochilus was automatically updated based on labeled data collected offline that day. We evaluated Trochilus' ability to maintain accuracy in such scenario. As shown in figure, Snort exhibits a significant accuracy decline of about 4% and 6% on the 10th and 20th days, respectively. This is because the existing rules are unable to cover new attacks. When Trochilus experiences an accuracy drop of 3% and 4% on the 10th and 20th days, respectively, its accuracy rebounds to about 90 and 7% on the 11th and 21st days. So Trochilus effectively keeps its accuracy high over time by automatically updating the system as new traffic patterns emerge or routes change. This demonstrates its ability to adapt efficiently to new traffic patterns. In conclusion, Trochilus is a learning-enhanced, high-throughput pattern matching framework. It replaces traditional pattern matching with efficient model inference. It integrates the power of machine learning with the high throughput and cost-effective advantages of programmable data plans. Through innovative techniques like BRN-based pattern modelization, semi-supervised knowledge distillation, and entry cluster optimization, Trochilus efficiently deploys high-performance models in resource-constrained data plans while ensuring automatic system updates. This is crucial for real-time adaptation to emerging network traffic and threats. Finally, evaluations shows that it achieves multi-Tbps level throughput while automatically updating to sustain high accuracy against evolving threats and traffic patterns. So that's all. Thank you. I welcome any questions you might have, and please feel free to email.